Hello everyone, I am Dhruva Kharka from National Institute for Material Science, Japan. Today I am going to share our latest research work on perovskite solar cell, in which we have done charge-modulated molecular passivation in amine-free, bromine-free perovskite solar cell. Before going detail, everybody know this perovskite solar cell has been improved device performance in a short time span from nearly 5% to more than 26.1%, and this improvement has been obtained by a number of ways. One is this composition engineering, and some work has been done on the strain engineering and 2D molecular passivation, STL and ETL engineering, and molecular surface passivation and multifunctional additive has been also used. And those different approach, this stability as well as the efficiency has been, and it is being explored in detail. And my talk is about the surface passivation, in this technique, and multifunctional molecules is deposited on the surface, and it might form 2D, it might diffuse through the grain boundary, and benefiting point is it not only improve the device performance, but it also improve the device stability as shown in this image. And these molecules can be diffused like here on the surface. It can be diffused through the grain boundary, or it's still on the surface. And in our case, we to understand its surface passivation effect, we try the vapor surface treatment by using MSCl powder, and we observe improvement in morphology, and it also change the surface chemistry. It cleans the metallic lead, and by this we improve the device performance from 12 to 15%, and then this is due to quenching of defect in the film. Here we had used P.PS as a STL layer, so efficiency is quite low. We tried to improve this efficiency by STL engineering. Here we use the PTA, which is very famous STL layer, and spot on nickel oxide, and with PTA we improve the device performance as high as 19.32, whereas in case of nickel oxide efficiency is not good as the PTA. But if we compare the device stability, it has the better device stability compared to PTA. And the reason is PTA is organic acetyl layer or polymer acetyl layer. With poor interface quality, it deteriorates the interface quality as well as the bulk layer with the aging, whereas nickel oxide retains bulk layer and the interface quality compared to PTA device. And then, but the efficiency of nickel oxide was lower, so we tried to improve it by modifying its surface. And to do that, we use the MU2PACZ sum layer and we treat this on the nickel oxide surface. In this result, the quenching of defect by which is observed by this photothermal deflection spectroscopy measurement technique, and it improved device performance from 15.6 to 17.2%. It is not so high, so we try to improve this further by modifying the bulk layer as well as the interface quality. To do that, we treat the nickel oxide surface as well as the 3D top of 3D perovskite by using multifunctional passivating molecules, and as well as we also change from two-step to one-step technique, in which by increasing the bulk thickness, and then we also use free perovskite material for the for improvement in device stability. And then along with that is as we compare the control film XRD, we can see here some remnant of PBI2 and formation of delta phase. And then to quench those kind of uh, this uncoordinated halide or halide site or lead site, and then to quench the remnant PB and delta phase, we source some multifunctional molecules, and we choose these two kind of multifunctional molecules having aryl and alkyl amine chains and dihalide. And reason of selecting is it's a difference in the basic basicity, and then due to different basicity it might interact with the uncoordinated lead site or halide site, and it might interact with the delta phase, so that it might quench those types of detrimental points that has been observed in the control film. And we have also positive points of different surface charge on these molecules. And interestingly, the surface of the surface treated film with the PADI and PZDI, so the significant difference we can see here some small crystallite. Those crystallite could be from the small crystallite form with the 2D phase. And to confirm those different observation in surface, we study the XRD pattern, and this XRD to have the comparative study, we also prepare the perovskite film with the mixed PADI, and we compare with the surface passivated perovskite film. We can see here with the PADI mixed film, it shows very high this characteristic peak below the 10. It means there is the formation of 2D phase, phase, and which explain the small crystallite observation in the PADI treated film. Whereas if we compare the same property with the PZDI treatment film, we can see very small crystallite form on the surface, and it means that this PZDI has less likely to form the 2D phase compared to PADI treated film. And that can be also observed with the by comparing the surface morphology of PADI and PZDI film prepared with the mixing these molecules. And it is also confirmed with the PL measurement, and we can see dominant peak with PZDI treatment, PZDI treatment, and it is so the formation of 2D phase. And we compare the device performance, but this is the device structure, this is the JB characteristic, and these are the device efficiency statistic. We found this device improvement basically guided from the this JSC improvement in JSC and JSC, VOC, and fill factor as well. And interestingly, the JSC for the PADI treatment is quite lower compared to the control film, and this could be due to the additional crystallite form that form on the surface, and that might reduce the JSC for the PADI treated film. And to confirm detail its effect on the surface chemistry or other characteristic, we study those film and device, and this shows the UPS spectra, and it shows the surface energy and of the control film and surface treated film. We found that this work function is increased with the surface treated film, and in onset energy also is increased. And this is the schematic of the work function and onset energy. And then we found that this surface treated film modified the surface energy, and To understand its distribution, we measure the topsin spectra, and this shows the distribution of surface-treated molecules in perovskite film. When we can notice here PADI treated film shows the uneven distribution, and somehow it diffused towards the bulk as well, might be through the grain boundary, whereas in case of PZDI, it shows uniform surface, uniform distribution on the surface rather than going inside. And this might be the reason for the effective quenching of defect which exists on the control film. Furthermore, we study the interface quality. How does it form the interface when we treat on the surface of 3D perovskite? We found that PZ, PADI treated film form more phase at the interface compared to PZDI treated film. It means due to densely formed 2D phase at the interface, it might lower the JSC of the film with the PDI treatment. Furthermore, we study the photophysics and defect physics, and for that we measure transient photovoltage, and this shows the longer carrier lifetime, longer for photovoltaic lifetime with the PZDI film, and this indicates the quenching or defect. And to understand the carrier profile, that also constitute the defect or other kind of carrier distribution, we found that PZDI treated film has lower CV density compared to control and PADI treated film. It means PZDI treated film is effective for the defect quenching. On those effect, we study, we analyze those things with the DFT calculation, and considering those surface charge, we are going to introduce some defect on the control film and try to understand it. When we found that the stark charge difference has significant effect on the interaction with the uncoordinated or lead or iodine or some halide kind of defect, and it also has this PZDI has also stronger binding energy compared to PAD molecules, so that could be the reason for the effective defect quenching. And these molecules also used for the different kind of perovskite system. This is wide bandgap perovskite, this is narrow bandgap perovskite. In both cases it worked effectively, and it improved the device performance, improving the JSC and BOC and fill factor as well. So it is universal, it is effective universally. And we also compare the device stability. Here, PADI film shows the better device stability compared to the control and PADI film, and the reason could be due to its difference in moisture tolerance. We found that PZDI treated has better moisture tolerance, and that can be that can be understood with the comparison of water contact angle. We found the higher water contact angle for the PZDI film after 1 minute, and then it reflect the its moisture tolerability, better moisture tolerability. And furthermore, we also compare the Moltke-Schottky plot to understand the interfacial deterioration. It shows the reverse and forward scan of Moltke-Schottky plot, and it shows the higher stresses compared to the PZDI treated film. It means higher stresses means it has the deteriorated interface, and it also shows the PZDI treated film has stronger or more rigid interfacial quality interface formation compared to the other surface treated or control film. And then this also shows the beneficial aspect of the VJTI treated film. And this is the summary, and we found that charge modulated amine derivative is effective for this modification of surface chemistry and modulation of surface energy, and it form the interfacial embedded 2D crystal line on the surface, and it attenuate the defect density, and it suppress ion migration. And finally, as a result of those characteristics, we improve device performance to 3.2% with the better stability. Thank you for your kind attention, and I would like to extend my gratitude to our collaborator and our colleagues who help to those work in my research. Thank you very much for your kind attention. Thank you.